Have you ever looked at a chemical name, something like sodium chloride, and thought, okay, cool, I get that. But then you see something like dinitrogen trioxide, and it feels like the rules just got thrown out the window, right? Well, guess what? They didn't. There's actually a really simple, kind of elegant logic behind all of it. And in the next few minutes, we're going to unlock it together.
So here's the plan. First, we'll figure out why there are even different naming rules in the first place. Then we'll dive into the two main paths that chemists take, one for compounds that transfer electrons and another for the ones that share them. And finally, we'll wrap it all up with a super simple guide you can use anytime.
All right, first things first, let's get to the bottom of this whole naming guzzle.
I mean, this is the big question, isn't it? One name is so clean, so simple. The other one's got all these prefixes like di and mono. It just feels totally random. But I promise you, it's not. There is an amazing reason for this difference, and it all boils down to the bond. And here it is. This is the big secret. It all comes down to the type of chemical bond holding the atoms together. So the very first question you always have to ask yourself is, what am I working with? Is it a metal plus a nonmetal, or is it two nonmetals? That one answer tells you exactly which path to go down. Seriously, think of it like a fork in the road.
So how do you know which path to choose? Well, you use this map, the periodic table. As a general rule of thumb, you'll find the metals over on the left and in the middle, and the nonmetals are hanging out on the right. Finding your elements here is the absolute first step. You literally can't name anything correctly without doing this first.
Okay, so let's go down that first path into the world of ionic bonds. This is the home of the givers and the takers.
With an ionic bond, it's all about a transfer, a handover. The metal atom is a generous giver. It wants to donate an electron. And the nonmetal is a happy taker. It gladly accepts that electron. This little exchange creates a positive ion and a negative ion. And then, boom, they stick together like tiny magnets.
So now that we know what they are, how do we actually name these things and write out their formulas? Well, it's a lot more straightforward than you might think.
Okay, so for writing the formula, there's this awesome little trick called the crisscross method. It's super handy. First, you figure out the charge for each of your ions. Then, and this is the cool part, you take just the number from the charge, forget the plus or minus for a second, and you crisscross it down so it becomes the little number, the subscript, for the other element. It's just a really quick way to make sure everything balances out.
Let's see this in action. It makes way more sense visually. Okay, magnesium has a 2+ charge. Nitrogen has a 3- charge. See how the 2 from the magnesium crosses down to become the subscript for nitrogen? And that 3 from nitrogen, it crosses over and becomes the subscript for magnesium. And just like that, you've got Mg3N2. Perfect.
And naming it, that's even easier. You just take the full name of the metal, no changes, so magnesium. Then you take the nonmetal, in this case nitrogen, you chop off the ending, and you replace it with "ide." So nitrogen becomes nitride. You stick them together, magnesium, nitride. See? Simple. No prefixes, no fuss.
Okay, your turn. Let's give one a try. If you were going to combine a potassium ion and a bromide ion, what do you think the formula and the name would be? Just take a second and think it through. And there you go. Potassium's got a 1+ charge, bromide has a 1- charge. They balance each other out perfectly, 1-to-1. So the formula is just KBr. And for the name, you take the metal, potassium, and add the nonmetal with that iodide ending, potassium bromide. You're getting this.
Now, like with any good system, there are a couple of special cases we gotta know about. Some metals, especially those transition metals right in the middle of the periodic table, are a bit tricky. They can have different charges. Iron, for example, can lose 2 electrons or 3. So to be super clear, we have to spell it out with a Roman numeral in the name, like iron 2 or iron 3. The other special case you run into are these things called polyatomic ions. Now, don't let the name scare you off. It just means many atoms. Think of them like a pre-made team. There are groups of atoms that are all bonded together, and they act like one single unit with its own special charge. The key here is to treat the whole group as a single piece. You never change their name or ending. You just use their team name as is, like sulfate or nitrate. This chart here is basically your cheat sheet when you're starting out. All right, let's hit rewind and go back to that fork in the road. It's time to take the second path. Welcome to the world of covalent bonds, home of the friendly sharers. So remember, this is the path you take when you have 2 nonmetals. Neither one of them wants to give up an electron, so what do?
They compromise. They share electrons to form a super stable bond. There are no givers and takers here. It's all about cooperation. And this fundamental difference is exactly why they need a totally different naming system.
You see, since these atoms are sharing, they can combine in all sorts of ways. Like carbon and oxygen can make CO, but they can also make CO2. So that simple crisscross method isn't going to work here. We need a system that tells us exactly how many of each atom are in the molecule.
And this is where those prefixes finally come into play. Mono for 1, di for 2, tri for 3, and so on. This chart is your go-to tool for naming covalent compounds. The name literally gives you the formula. It's like a recipe that says, okay, take 2 of this atom and 3 of that one.
So let's try it out. If I tell you the name is dinitrogen trioxide, what do you think the chemical formula is? Just translate the prefixes. That's it. Di tells you there are 2 nitrogen atoms. Tri tells you there are 3 oxygen atoms. So the formula is simply N2O3. It's a direct translation. And this is exactly why water, H2O, can be called dihydrogen monoxide. 2 hydrogens, 1 oxygen. Makes sense now, right?
Okay, so we've walked down both paths. Let's pull it all together into one final super simple guide. This table right here, this is everything. It puts the whole decision-making process in one place. It all starts with that one question: metal plus nonmetal or nonmetal plus nonmetal. Your answer tells you if electrons are transferred or shared, and that tells you which naming rule to use. Simple names with IDE endings for ionic or prefixes for covalent. See? It's not random at all. It's a beautiful system. You know, we just took a pretty confusing topic and made it simple, all by learning to ask the right first question. Is it ionic or covalent? It really shows you the power of just sorting things into the right buckets. It makes you wonder, right? What other complex systems, whether it's in biology or technology or even our daily lives, are just waiting for us to figure out the right first question to ask?